Good morning, all. So today our discussion will be on mathematical model in design. So before starting the topic, I would like to say that few of the topics, right, we have already discussed, right. I have to do a recap. So better that we will do once we have completed the module 3, right. So most probably by next week, Tuesday, I'll complete the module, and then we can have a recap of it. Okay. So now let us start our discussion on mathematical modeling in design. This particular topic is somewhat interesting because for a problem or for a particular requirement or a particular problem, how to do a mathematical model, how to design a mathematical model. Such a kind of things we are going to discuss, right? In a general way, not too much of a mathematical point of view, but still in a general way, right? So let us start a discussion, right? Fine. So what is the need for this mathematical model, right? So the need for the mathematical model is that, say for example, you are going to lift what do you say a weight, right? You are going to lift a weight with the help of a rope, right? The you are going to lift a particular object. Let us say you're going to lift a particular object. The weight of that object is say 200 or 300 kilograms. Okay, and using a help of a rope, you are going to lift it out, right? So how are you going to lift it? Okay, so this is what the situation, right? I'll repeat it. You have a object. That object weight is around 300 kilograms. Using a rope, you are going to lift it, and you are lifting it to say 10 meters. Okay, so now you have to think in a mathematical point of view. Simply, you cannot tie a rope. Tie a rope into that particular object, and then you cannot lift it because it is around 300 kilograms, right? Simply, you cannot take a rope and you are just simply tie it out, and you cannot lift it out. Okay, so you need to have a mathematical model. Okay, so that is what mathematical model are central to design, because we have to be able to predict the behavior, right? The reason is that normally mathematical model will predict the behavior of the devices, right? An example I told you, you are going to lift that particular object with the help of a rope, okay, and the weight of the object is 300 kilograms. So if you are using a rope, right, whether the rope will sustain, right, what sustain in terms of stress, right, and strain, right? Say for example, if you are lifting a rope and suddenly at the fifth meter, right, 5 meters you have lifted it, no problem, and once you're again lifting, trying to lift it, what happens if the rope get, what is that, cut down, right? Then it's a big difficult, right? Big issue, right? So to avoid that, what actually you are doing is that you are predicting what kind of rope I have to use, right? What is the elasticity of that rope, right? So if the elasticity exits, it will cut down. So so how much the elasticity of the rope should be to lift a particular object, and the weight of the object is 300 kilograms. How much distance you are going to lift it out is 10 meters, right? So you are predicting the behavior of the devices or a system that we are designing. This is what is called as the mathematical model, right? Not only in this particular case, you can take anything, an airplane which is flying, a building, right? A 20 floor, 30 floor building. If you're making if you're building a building, right? So if it is 20 or 30 floors, so for each and every real time problems, right, you can design or you can create a mathematical model. Okay, so what are the things you have to ask, right? So you have to ask, how do we create mathematical model? Okay, how do we create mathematical model? And once you have created the mathematical model, how do we validate such models? Okay, you have to validate it whether it is correct or not, right? Okay, and once you have validated and once you come to a conclusion that the mathematical model which I have created, right, or which we have created is correct, then how to use it? These are the three major questions you have to ask while you are designing a mathematical model. Okay, so three questions: how do we create the mathematical model, how do you validate it, and how to use it? So these three questions normally it should be asked when you are designing a mathematical model. Okay, and also you can have, say, are there any limits on their use? You can have a limit, right? Say, for example, this much of elasticity for that rope. If you exceed it, what happens? The rope will get cut down. So you should have a limit. You should have a limit. So these are the limits. Okay, you should not exceed this. You should not. What is that? This is the limit of selecting a rope. Likewise, you can have a limit of it, right? So all these things you can have a question on it. I mean, you can analyze it. Analyze it. That is what you are designing a mathematical model. Okay, fine. Okay, so now let us move to the next point, that is basic principles of a mathematical model. Okay, so normally, let me do one thing. I'll stop this video, right? Before that, I'll explain you what is that basic principle of mathematical model. So normally, right, in a mathematical modeling, first, this is what happens. That is, there will be a real life, real time or real world problem, okay, or real world phenomena. Let us say it is the phenomena, right? So what you will do is that you will observe that phenomena, right? And once you have observed it, based on the observation, you will create a model, right? Once the model is done, right, is what the analysis is done, you will do the predictions, right? Once the predictions are done, then what you will do, you will apply to the real world phenomena, right? Right, I'll repeat it. You have the phenomena here, right? You have the phenomena here. That phenomena is actually a problem. Let us say a problem. You are observing that problem from the real world, right? Based on the observation, what you are doing is that you are modeling it. Once modeling is done, what you are doing is that you are doing the predictions. That is what the mathematical model, right? The based on the predictions, you are applying that model, mathematical model, to the real world phenomena, right? This is what actually happened here. Okay, so normally in basic principles will be, first you have to when you check that real world phenomena, first thing is you'll be asking question, why do we need a model, mathematical model? First question you'll be asking it, right? Why? Okay, so let us take this example, right? Okay, one second. I'll repeat the video so that you can able to understand it. Fine. So now you are seeing, right, your a crane, right? Your a crane is actually lifting 750 kilograms of weight or an object, right? Of an object, right? It is lifting. Okay, fine. Now, so you have a thick metal rope, is it right? You have a thick metal rope, and you're lifting it out, is it right? Excellent. Right. So load does not break the rope under the stress, because the stress produced by the load is less than the elastic limit of the rope. Okay, the load does not break the rope. See, it's a very small rope, right? But your object is around 750 of kilogram of weight, right? So now the thing is that the rope should not, rope will not cut, because the stress produced by the load is less than the elastic limit of the rope, right? Elastic limit of the rope. That is why the object is not cutting down the rope or break down the rope, right? Fine. See, this is what the cross-section view of different ropes. So the cross-section of the view of different ropes, actually what actually it is mentioning is that this cross-section of the rope is defining the elasticity of the rope, right? But you have to calculate the elasticity, even though if it is for 750 kilogram of weight, this elasticity is fine. For example, say if you're increasing the load to say 1500 kilograms, Sometimes, right, this elasticity is not enough. So you have to calculate that elasticity also, right? So when you are uh, designing a mathematical model, first thing is, why do we need a model? Why do we need a model? That is, you are observing the real world phenomena and then you are developing a mathematical model. So because of this particular real world issue, we need to have a mathematical model. Okay, so first you have to ask the question, why do we need a mathematical? If you have the answer, then you can go for the mathematical model, right? For what will we use the model? Right, so what will be, so for what will be, so here in this case, in this particular what is that real world phenomena, right? We'll what will be using this model, right? So you will be calculating the rope elasticity, right? Whether it is possible to lift this particular what is that object, right? So usage, so we will be answering in the case of usage, right? Okay, we are going to use this. Okay, so what do we want to find with this model? Okay, uh, so what kind of let's say, for this particular model, for this particular real life what is that real life scenario, right? We have developed a model and we understand that, okay, for this particular purpose we are going to use the model, right? So ultimately, because of this mathematical model, what are we going to find? What are we going to find? So we are going to find many things. For this weight, for this particular weight, or for this particular object weight, we need to have this much of elasticity for a rope, right? That we are actually finding out. So, right. So why we are using this model? For what we will be use the model, and then what to find? What are we going to find? That also we are going to do it, right? It's fine. The fourth one is, what data are we given? Right? What data are we given? Say for example, we'll be having some physical quantities for this particular case, right? We'll discuss that in detail in the next coming slides, right? It is, since it is a general discussion, I'm telling that what data are we given? What are the physical quantities? For example, say if you are calculating the force, then force means force is equal to mass into acceleration. Is it right? So what are the physical quantities? Mass and acceleration are the physical quantities. So what are the data are given? Right? That also we have to know it out. Okay. Then what can we assume? Right? What can we assume? So assumption. Say for example, for 10 meters, for lifting this particular object, 750 kilograms of object, we have to assume, okay, we can take this particular rope. Okay, so we can have some assumptions, right? So what are the things we can assume? Okay, so how should we develop this model? What are the appropriate physical principles we need to apply? Okay, say for example, in this case we can apply what Hooke's law, is it right? We can apply Hooke's law. Okay, fine. So physical principles, what are the physical principles we can apply? Okay, and what will our model predict? Of course, right? What will our model predict? Can we verify the model prediction? Yes, whether our calculations are correct, whether we can able to verify that. Okay, and the predictions, whether it is valid or not. Okay, and can we improve the model? So for all these questions, right, we need to have the answer. Then only we can go for the mathematical model, right? So ultimately you have a real world phenomena, you are designing a mathematical model and you are applying it to the real world phenomena, right? Observing, modeling, predictions, and then applying, right? This is what your what is that basic principles of mathematical modeling, right? Fine. What do you mean by abstractions? Abstractions, scaling, and lumped elements. So in mathematical modeling, first we should know about three major terms. One is abstractions, then scaling, and lumped elements. So what do you mean by these three things? Let us discuss that. Okay. So abstraction. So from the name itself, you can understand, is it right? Abstraction means uh, you have, let's say you have um, You have a big problem. You have a big real-time problem you're having, right? So how to convert that real-time problem into a mathematical model? That is, you are reducing that into a small mathematical equation, right? That is what is called as the abstraction. Okay, so thinking about finding the right level of abstraction. Abstraction means what? Detail means identifying the right scale. So that is what the comparison between abstraction and scaling, right? That is an important decision in modeling is choosing the right level of detail for the problem, which thus indicates the level of detail for that model. Okay, so let's say Hooke's law. Okay, Hooke's law represents f is equal to k into x. Okay, so what is k here? K will reflect the stiffness of the particular rope. Let's say stiffness of the particular rope. Okay, and let's say x represents what? So in this case, X represents uh, the load deflections, right? That means you are describing the static load deflection behavior. Is that right? For example, say in our case, we took 750 kilogram of weight. Is it right? So of that object, and you are lifting with the help of the rope. Is it right? So what actually you are doing is that you are um, calculating the what is that load deflection behavior, is it right? Load deflection behavior, right? And in this case we are using that Hooke's law, right? In the which is actually the physical representation of it, right? So Hooke's law, what actually is telling? F is equal to k into x. So k, what I told, it is the spring constant, right? So the interpretation of k incorporates the detailed properties, right? Detailed properties of the rope, for example. Okay, so let us say, let me take another example. I'm going to um, design a ladder. Okay, a ladder step. Okay, so for that ladder, right? Say for example, that ladder will what is that? Will say for example, say a person who is having say 70 kilogram of weight can use that ladder. If he is climbing in that ladder, the ladder won't break. But if the person who is having a weight of say 90 kilograms, and if he is using that ladder, the ladder may break out. Is it right? So how do we calculate this? So how much this particular ladder will withstand? How much weight this particular ladder will withstand? That we can able to calculate with the help of the Hooke's law, right? So it can be Hooke's law can be used to describe the static load deflection behavior of a ladder step. And we told that Hooke's law represents F is equal to K into X, where K represents the spring constant. Is it right? So the spring constant K will reflect the stiffness of the step taken as a whole. Is it right? Right? Fine. So this interpretation of K incorporates detailed properties of the step, such as material of which it is made and its dimension. Is it right? So the material of which it is made. So which material it is made, and also the dimension of it, so that you can able to withstand the particular weight of a particular person. Right? This is what is called as the abstraction. So ultimately, what is maybe abstraction? You have a big real-time problem, and you are converting that problem into a smaller level of it. That is what the abstraction, right? And it is possible to what is that? Think that particular abstracted level, right, in a bigger scale or bigger level. That is, detail means of identifying the right scale, right, for our model with respect to the quantity of size measured. Is it right? So you have an abstract level of that particular problem, and that can be scaled to a bigger level or a higher level. Is it right? For 100, so that is what I'm telling, right? So 100 kilograms of weight, or say 350 kilograms of weight, and this much of rope, this much stiffness of the rope, right? If you're if you're having that measurement, right, we can able to easily apply it to the real life scenario. Is it right? This is what your abstraction and scaling. Okay, we'll let it, don't worry, we'll have a discussion with the help of a what is that formula or problems, right? Fine. So once that is done, right, uh, we can able to apply it to the real life scenario, right? Fine. The third concept is what is that? Third concept is lumped elements. What do you mean by lump? So lump means, say, I'll give an example. You have many small materials. Let us say, take an example of circuits, right? What you're having the circuits, you have resistors, capacitors, what do you say, inductors, right? So, and then batteries, right? So many things are there, right? These are all small physical components, right? What you are doing is that you are combining all those components to generate a particular concept, right? So you are compiling together a lot of information about how the particular scenario is framed. Okay, a circuit represents some particular for example, say you have a circuit for glowing a light. Okay, so for that, what are the things you require? You have a circuit, right? You have a circuit. In the circuit, what you are having, you have different components. That components are grouped together or lumped together. This is what is called as lumping. Means what? You are grouping together to achieve something. Is it right? To what is that? Glowing a light. Okay, so that is what is called as lumping. That is compiling or lumping together a lot of information. Is it right? This is what is called as lumped elements. Okay, so three things we have discussed. Okay, what is that? Abstraction, scaling, and lumped elements. So what do you mean by abstraction? What I told about abstraction. Abstraction means your detail of the problem is converted into a smaller size. That is what is called as abstraction, right? And then what you are doing, you are scaling it, right? Scaling means what? Thinking about the magnitude or size of the quantities measured with respect to a standard. So, right? Fine. Let us see an example. Don't worry, you will be able to understand clearly. So, abstraction means smaller level. Scaling means you are mapping it with the real-time scenario. That is what scaling it. Okay. Then simplifies the description of the behavior of spatially distributed physical systems. Okay. So you have many distributed physical systems. You are combining together, which is called as the lumped elements.